Okay, we are all set. Welcome and good afternoon. Thank you very much for coming. It's a great pleasure to have you here. And we have some fun activities, some presentations planned for you. So some ground rules first. Please, can I ask that you keep your phones in silent? Yes. And also, we're not expecting any fire alarm. So if the alarm sounds, please follow the stewards out of the building towards the parking. Okay? And if you have any questions, please raise your hand. But after the end of the presentation, if you can stay longer, we're happy to talk to you about any questions you might have during the presentation. And also, our younger audience members might have been given a raffle ticket. Hold on to that raffle ticket because there will be prizes in the end. Okay, excellent, yes. So I've been told I should be in this proximity here. So if you see me going away, please, so I can come back because it needs to be recorded. I will be starting the presentation, and then the team of colleagues will be taking over from me. So then we have Jenny. Up and say hello. We have Jenny, we have Jeff, and Johan and Patrick will follow on. Yes, everybody's here. So let's see if it's working. Yes, it does. So first of all, a few things about me. Who am I? So my name is Vangelis. It's not an English name, it's a Greek name, in case you wonder. And I'm already away where it's supposed to be, sorry. Yes, that doesn't go well. So I'm a senior lecturer in chemical engineering. Okay, so my day-to-day job involves three things. Okay, I do teaching. I teach chemical engineering students. And for example, I teach them how to design chemical reactors that make, for example, a drink, and how to design these reactors without explosions, which is a useful thing to know. I also do research, like every academic. I love my research. I'm passionate about research, and I will come back to that later on in the presentation. And the third thing I do is what I'm doing now. Okay, I do outreach, we call it global. So what I do, I travel across the country or in Europe, which is fun, to tell students about engineering and why engineering is so important about shaping our world and the world that we live now and the world for future generations. So let's start with a question. I'm an academic and I enjoy asking questions. So what is an engineering? And I can try to give you a hint. So I have these two pictures. I have a lovely lady on the left with a white coat and this guy and lady with the high-vis vests. So raise hands who you think is an engineer. So is the lady on the left an engineer? Any hands? No? Can be. The guys and the lady with the high-vis vest, engineers? Yes, majority, yes. So engineers usually look like that when they are out in the field and they work. Okay, I'm an engineer, but I don't wear high-vis vest. Okay, so yes, engineers work, and we will see what they do. So what do engineers do? And why do we actually need engineers? Okay, let's start actually think what engineers do. Engineers build stuff. Okay, so an engineer will build this wonderful bridge or the Shanghai skyscrapers. Okay, so engineers build stuff. Even the building that we are today has been designed by an engineer. What else? Let's see. A lot of day-to-day objects. So for example, your lighting, your medication, your food, the food packaging, or all the electronic devices are being built by engineers, designed and built by engineers. What else engineers do? Engineers also design and build whatever moves, flies, or swims. So pretty much, engineers do everything. So the world as we know it today is designed and built by engineers. And the interesting part is that, like to build a car, this nice black car, I think it's a Bentley, okay, you need a mechanical engineer to build the chassis and the engine. You need a chemical engineer to build the battery of the car. If it's an electric car, the whole electric motors as well. We need an electronic engineer to work on the motors or the air conditioning or anything electronic in the car. Then you need a civil engineer to build the roads that the car drives. And then you need a marine engineer. If you're going to drive to an island, you need a boat to get there. So a marine engineer will design the boat. So engineers, even though we have different disciplines, we all work together to build stuff. Okay, so from all these things, I think it's quite convincing that engineers build stuff. And what else engineers do? And actually, why do we need engineers? Because if we did not have engineers, we would not have all this nice stuff. The buildings, the day-to-day items, or everything that we use to move and travel. This is a little bit more scientific interpretation of what an engineer is. But actually, engineers solve problems. Okay, if there's a takeout message from today, is that engineers solve problems. And we will see some of these problems in a bit. So if you're going to come and study engineering in Newcastle, this is what we've got. Chemical engineering, electronic, electrical, mechanical, civil, marine, offshore, and some sea technology. So all these disciplines you can do at Newcastle. Now, in all of these, you need to be good at maths, okay? Do we love maths? Yes. Excellent, yes. So you need maths, that's very good. Now, if you're going to study chemical engineering, we also require chemistry. Okay, so if you want to study any engineer discipline, maths is good. If you want to study chemical engineering, maths and chemistry is good, because it's on the name, it's chemical engineering. Now, this is the part where I said I will be talking about my research, okay, and the research that a chemical engineer will do. My colleagues afterwards will talk about research in their own subject fields. Okay, so why do we need research? We need research because we have open questions. We have problems that we don't know the answer to. Problems that affect our daily life. So, have you heard about climate change? Yes. Have you heard about carbon dioxide? How many of you know that carbon dioxide actually is one of the reasons that we have wildfires and wild weather, climate change? Raise hands. Yes, everybody knows that. Excellent. So, fires are not good. Okay, we have fires in Los Angeles now, devastating. And I'm Greek, and Greeks are good at one thing. We're very good at burning our forests. Okay, by the rate we burn our forests, my grandchild will not be able to see a forest in Greece if we don't do something about it. Okay, so engineers need to find a solution. Something that people say it's going to be very effective is that if we can take this carbon dioxide out of the air, then everything will be better. Okay, that's partly true, but it's one way of dealing with the problem. We call this direct air capture. Have you heard this term at your school? It's a bit more, not for schools, but this is that's an engineer working here. So what we're trying to do is we try to take carbon dioxide out of the air. So people build these huge devices. Okay, even though that looks magnificent, has all these fans and is huge, it can only take carbon dioxide out of the air that is being emitted by a few cars per day. Given the fact that we have hundreds of millions of cars around the globe, this is not going to work. So this is where research comes. Okay, so a chemical engineer, and like myself, will try to find solutions to this problem. So what I'm working with is I'm taking inspiration from biological system, from cells. So apparently, human cells have found a mechanism that can actually take nutrition out of your bloodstream. And we can monitor actually how they do that and apply the same techniques, the same mechanistics into a device that takes carbon dioxide out of the air. Okay, so this is a problem, and we try to engineer to design a solution. Okay, so that's, for example, what a chemical engineer will do. Another thing that a chemical engineer will do will be pharmaceuticals, medicine. One of the examples is fighting COVID. How many of you had COVID? I had 3 times. I got all the variants. Okay, and how many of you had a COVID test? I had a lot of them. I had at each one of them. Okay, the problem with the COVID test is they will stick something in your nose and will try to take some sample, and then you will see you have a negative test, and you're all happy, you go to the school, and then you transmit disease to other people. The problem with that is that the COVID tests were not very reliable, because the COVID tests were very good if you had a lot of virus in your saliva. If you don't have a lot of virus in your saliva, it will give a false negative result. Okay, so what a chemical engineer will do, and actually that was a lady, Peter Marlowe, did this for our school here. She devised a more accurate COVID test. Okay, 6,000 times more accurate. So you need 6,000 times less virus in your saliva to be able to detect the virus. So this device now is patented, it's out in to go to sale, and the idea is that, do you know how many people globally had negative tests that were faulty? Around 1 out of 3 people was tested negative and it was false because of that. So a chemical engineer will find a solution to this. There is a problem and we design the solution. So these are 2 of the areas that chemical engineers will work with. Exciting? Good. So that's my last slide. Oh, there is music. Do not expect that. Yeah, a bit of music. So this is, I'm not sure if you know the Stephenson building. This has opened last year, and it's an amazing building for engineering. So engineering students have the chance to study in these amazing facilities and do all of their work. And I think that video is how this building has been built. It took a couple of years. Unfortunately, I don't have a fancy office in that building. I'm still in the old building. But if you have the time, please do come with your parents and visit the building. It's really nice. And if you actually want a more personalized tour of the building, please don't hesitate to email me. I'm happy to walk you around. So that's for me. Okay, and oh, I'm running late. So Jenny, you're next. Sorry. Yes.
Sorry, cutting the music off, everyone. Can everyone hear me okay? Yeah, okay. Thank you, Evangelist, for that. It was really interesting to learn more about chemical engineering, and I actually learned quite a bit there as well. So my name is Dr. Jennifer Olsen, and I'm actually a different type of engineer. I'm a biomedical engineer, and I'm going to tell you a little bit about what it is I do in my day job, and perhaps help you decide whether one day you might like to be a biomedical engineer too. So when I was younger, I had no idea what I wanted to do when I grew up. I want to be a doctor, I want to be a vet, I thought about working in a shop, I want to be a fashion designer. And it was only once I was 16 that I actually started to panic a little bit, because all of my friends were applying for jobs, or they were applying for apprenticeships or universities, and I still didn't know what I wanted to do. But I did have a list of things, I just didn't know what the job title was. So I wanted a job where I could be creative, I wanted a job where I could make things and build things, because I really liked practical hands-on skills. I wanted a job where I could help people, but I knew that I did not want to be a medical doctor or a surgeon, that just wasn't for me. And I really liked maths and science, but I only really liked it when it was practical, when I could apply it. And so this was things like, you know, working out discounts in shops or working out the probability that I would win a competition. And it was actually a competition that helped me decide. I saw a poster for this competition, National Engineering Competition, but the theme was healthcare, and the task was to design a new device that would help people live a more healthy, a more active life. And this was just a complete light bulb moment for me. I'd looked at things like wheelchairs and pacemakers and hearing aids, and I'd never once considered how they came to exist. It didn't occur to me that engineers worked on these things. And from that moment onwards, I just knew exactly what I wanted to do. That was for me. As soon as I knew that was a job, I was away. And that's why I want to tell you a little bit about what it is that biomedical engineers actually do in their day job, so you can decide maybe if that's for you too. So before we start, I'm just going to cover some new words that you might not have seen before. So when I say limb, I mean someone's arm or someone's leg. And an amputee is someone who has had either their arm or their leg removed through surgery, if they've had maybe an accident or a health condition. And some people are just born without all of their limbs. And those people might choose to wear something called a prosthetic limb or a prosthesis. Here we've got a prosthetic arm. And there's 2 key things that I want you to remember, okay? So there's 2 key parts here. The socket, that's the part that attaches to the person. And then if it's an electric prosthesis, something powered by a battery, it'll have this special kind of sensor called an electrode. So if you can just keep those 2 things in your head, you'll see why in a bit, because I'm going to show you a video. But just first of all, I want to cover that sometimes people don't want to wear a prosthetic limb, and that's completely okay. They find that they're happy without one. But for the people who do, that's where I come in. And you might have actually seen some before if you've watched the Paralympics. You might recognise the runner Johnny Peacock, or if you like motor racing like I do, you might recognise Billy Munger. So I'm just going to show you a quick video now. I filmed it with my friend Shinny, who's also an engineer, and I'm just showing her what I do.
So at the moment we have a prosthetic hand over here, and we also have some little sensors. These are called myoelectrodes, which is basically just a little sensor that measures your muscle activity. The hand needs instructions. You would need to tell it when you want it to open, when you want it to close. Yeah. And one of the most convenient ways to do that is to just use our own natural muscle activity.
Your brain can still give your muscles instructions,
yeah,
but then those instructions are transferred to that,
yes,
and that tells something like that what to do.
I'm always doing. That's you.
What's your specific focus?
We've got these sensors that obviously wouldn't normally be attached to your arm using stickers, that normally just be recessed into the socket wall. What I'm trying to do is design prosthetic sockets that facilitate that connection better. So how can we change the shape of this, or change the design of this, maybe change the materials? If I can facilitate that reliable connection between machine and person, it will make the devices a lot more reliable, that my colleagues have then got a reliable signal to work with.
So I talked a lot there about reliability. So when an amputee is wearing their prosthetic arm, they need to know that they can trust it. If they pick up a hot cup of tea or something valuable like their phone, what's going to happen if their prosthetic arm doesn't work? Are they going to drop it? Are they going to hurt themselves? So that's what I've been working on for quite a few years now, is to try and make them more reliable. But I've been very lucky in my job. I've got to work on a lot of different projects. So I was just going to tell you about some of the other things as well. So over here, we've got my friend Chris. He plays the French horn. He's a professional French horn player. He's also a double amputee, and he has a disability that gives him a lot of pain in his hands. And it was starting to affect his ability to play and his ability to support his French horn. So he got in touch with the university and said, can you guys help me? Is there anything you can do? So as a team of engineers, we got together and we built him a custom stand that allowed him to still play in his classical style and move his French horn freely, but would take all of the weight off him. And that was a really fun project to be involved with, and Chris has been involved in loads of projects since. But completely at the other end, I've also worked on devices that go inside of the body. So if your knees start to hurt or your hips start to hurt, you might go and see a surgeon and have it replaced with an artificial one here. And they're meant to last about 10 years, okay? But the thing is, sometimes they don't last 10 years. Sometimes they only last 1 year or 2 years. And it's my job to figure out why, so that when people have a surgery, they know that they're not just going to need another surgery in a year's time and be in a lot of pain. And most recently, I've actually been working with researchers in Malaysia and Singapore to see if we can make prosthetic limbs cheaper. Because at the moment they cost a few £1,000s, and that's out of budget for a lot of people. So we're trying to make new materials and design them in a different way so that everyone can afford one. So, have I convinced anyone? Is anyone interested in being a biomedical engineer? I'm seeing a few hands. Okay, that's good. That's reassuring. Well, if you do want to be a biomedical engineer, you might be thinking, how can I become one? Should I study biomedical engineering? Well, it is possible, but it's actually quite rare, because in general we have these defined disciplines in engineering: mechanical, electrical, civil, chemical, and you'll notice biomedical is not on there. And that's because it's quite common for you to train as something else first, like an electrical engineer or a mechanical engineer, and then focus your efforts towards healthcare and towards helping people. And for that reason, it's not uncommon to see doctors, neuroscientists, surgeons moving towards working biomedical engineering too later in their careers, because they share the same problem-solving mindset that we have. And actually, we're going to hear from other speakers tonight, Patrick and Johan, and they're going to talk to you about other things that they do, but I'd also like to highlight some of their work that they do that fits within biomedical engineering. So Patrick, even though I would say he fits within the domain of electrical engineering the best, he works on helping people who've lost their sight restore their sight with devices. Similarly, Johan, even though again also in electrical engineering, he's working on medical devices that people can take into their homes so they spend less time in hospitals and more time recovering with their families. And you've already heard enough about what I do. So I just want to say thank you for listening. If you'd like to see the full video, it's there. And you're going to hear from a lot of different kinds of engineers tonight, and I just hope that you leave knowing that if you have the problem-solving mindset that engineering is absolutely for you, no matter the discipline. Thank you.
So, hello, my name's Jeff, and I'm going to talk to you about a completely different type of engineering, a completely different environment, and that is underwater or subsea. So, I'm a professor of acoustic signal processing. You'll see why that's significant in a moment. I'm an electronic engineer by training. I'm from North Shields. I'm local, as you probably guessed. And when I finished my degree in electronic engineering, I joined a team which worked on this problem of how do we communicate underwater? How do we track things underwater? How do we find things? How do we image things underwater? So there's a whole world of communication technology that you take for granted every day. You've got a device in your pocket probably that can connect you to anybody in the world, download broadband, high quality video images and all kinds of things. And you take that for granted. But one of the things we'll find is that all of that technology, brilliant as it is absolutely no use to us at all as soon as we go underwater. Okay? And if there's one thing that winds me up, it's Hollywood movies where you see somebody on a standard walkie-talkie talking to somebody above the surface, so from the bottom of the sea to above the surface. And that does wind me up a bit, because if any of that worked, I've wasted my entire life. Okay? So why do we think we can't use radio communication underwater? What is it about water, and especially seawater, that we think's a problem? Yeah?
The seawater has salt, and if you put your phone into water, it turns water on fire.
That's pretty good. You're on the right track. Anybody else? Yeah? Kind of, yeah. So the big problem with water is that it conducts electricity, especially when it's seawater with salt in. So radio waves are an electromagnetic field. And if you put an electric field across something that's conductive, then electric current flows and the field collapses and disappears. So that's essentially why we can't use any of this technology. So your Wi-Fi, your 4 and 5G, your Bluetooth, all these technologies have a range of a few centimeters through seawater, which obviously isn't much use at all. As well as that, things like radar and GPS navigation that we all rely on are no good either, because they don't work underwater for the same reasons. However, there is an alternative that works very well. Does anybody recognise what these sounds are? Yeah? Very good. Well, there's two things going on here. These clicks you can hear, the clicking noises, that's echolocation by dolphins. That's how they navigate around their environment and find their food. The other thing is the whistle noises you can hear are them sending messages to each other. That's them talking to each other. And in fact, you'll see these patterns repeating. They're what we call signature whistles. These are like the dolphin's call sign, and you can recognize individuals from them. So sound travels very long distances underwater, and basically I've spent my career developing devices that use the same techniques to send data through the water, to find out where things are underwater, and to image things underwater. So this leads on to what we call underwater acoustic technology, using sound waves to solve these big problems. So first of all, we've got devices that we call acoustic modems. These are like our mobile phone or our radio transmitters and receivers that allow us to send data over many kilometers through the water. So that allows us to connect to sensors and allow divers to send messages to each other, for example. Then we've got positioning, so we can create technology a bit like GPS underwater, so we can precisely find where things are and allow us to navigate and not get lost. And you'll see where that comes in a moment when we talk about underwater robots. The other thing we can do is, like the same way radar finds things out in the air, well, sonar finds things underwater and can actually produce quite detailed images of things underwater. So there's an image of a shipwreck. So there's a very famous shipwreck. What's the most famous shipwreck in the world? Yeah? Yes, good guess. So that is the bow of the Titanic, 4,500 meters down. Far too deep for anyone to go with a diver, so you need robots or very special submersibles to go anywhere near it. But from a long distance away, you can see it with a sonar, whereas you can't see it with your eyes until you get very close to it. And so we rely on that to find things underwater. So this is all very challenging, and we use very clever signal and image processing techniques, very clever software algorithms that allow us to take these complex signals and extract the information we want from them. So it's a very challenging problem, and that's really what I do in my research. So to give you some examples of the sort of projects I'm working on, the current applications. So big part of it is this problem of how do you navigate and track an underwater robot. So that's a small underwater robot that we call an AUV, an autonomous underwater vehicle. It's about this size, and it swims around on its own, gathering data from the environment. So this is things like environmental data, so it's got all kinds of sensors on it. And I just started this little video. So that little device on the nose is our communication device, and that allows us to send messages to control the robot, get data back from it, but also to track exactly where it is. And that little track you can see there is this robot swimming around in what we call a lawnmower pattern, swimming up and down, gathering data off the seabed, and we can track exactly where it is at any one time, and also it knows where it is, so it can navigate. So that's commercial products, and there are thousands and thousands of these systems operating around the world based on technology developed at Newcastle, and technology I've been working on since I was 21 years old, which is a long time ago now. The other cool thing we've done is got divers and robots to work together. So diving's quite hazardous and difficult. What about if you had a robot to help you, to carry things for you, to sonar image the environment and tell you what's out there? So this is a project where we had a diver and a robot working together, and our communication technology allowed the diver and the robot to talk to each other, to exchange data. It allows the robot to know exactly where the diver is and follow the diver around, and they work together as a team. And the diver can bring the robot over, give it something to take up to the surface, or get the robot to go and collect something. So they're working together as a team, and that's a really cool project. And one of the things we've done most recently is used our technology to combat a really big problem, which is marine plastic pollution. I'm sure you're all aware we've got a big problem with plastic in the oceans. And one big source of this is lost fishing gear, fishing nets, fishing traps. And we developed a very affordable technology that can be attached to fishing gear, so nets and traps. When we put them out there, we can put a little transponder on there, and that allows us to find it very accurately again if it's lost. So last year there were some big storms in the North Sea, lots of gear was lost out in the North Sea, and thanks to our technology, some of that equipment was recovered. We're trying to ramp up the use of this technology so that the majority of fishing gear lost at sea will be recovered in future. But that's all I wanted to tell you about. There's a link there if you're interested in finding more about this project in particular. But this is technology that's captivated me for 30 years now, and it's taken me all over the world doing experiments. So it's been a really exciting branch of engineering to work in. So I'll leave it there.
Hi guys, thanks for being patient with a slight disruption. Okay, so firstly I'll talk a tiny little bit about myself, and then hopefully we'll get away from that and get into some stuff about semiconductors. So I'm Dr. Johannes Gorsden. I work here part-time as a researcher, part-time as a lecturer. My background is physics and materials, but during my PhD I did a lot of work on semiconductors, which is mostly silicon to you guys, but I did some work on graphene, which you might have heard of. And then I've kind of segued here and there and ended up in bioelectronics, medical electronics, and bits and pieces here and there. So that's it. Oh, and one other thing, I've spent a lot of time working in clean rooms, and why I say that will become clear soon. So you might think it's a bit weird that I'm starting a lecture about semiconductors with a picture of the biggest building in the world. And it's because I think when we think about the biggest achievements in engineering, we often think about the big several... Question? Already? Gold? Oh, excellent. You're correct. I was just about to say that. Do you know how tall it is? It's 828 meters tall. Very good. I had to look that up this morning just to get it all in my head. And it's actually bigger than our local biggest hill, the Cheviot, and it absolutely blows my mind that people have managed to make structures that are so large. But they've been doing it for a long time. We've got the pyramids of Giza. These were built somewhere around 2600 BC, and they're not 828 meters tall, but they are pretty big, somewhere around 300 meters, I believe. And finally, we've got our 16-kilometer bridge between Denmark and Sweden. So buildings are pretty cool, and they're very big achievements. But actually, what I think is the biggest achievement that humanity has managed to do is the home computer, or more specifically, the chips inside the computers. And now we're looking at the very small. First, we're going to have a little foray into the world of fashion. And here you see some of our students. Fortunately, I haven't been photographed in a Tyvek suit, but these are the Tyvek suits that we wear when we're working in our clean room environment to make things on silicon chips, which are very, very tiny. And why do we think we might need to wear such appealing apparel for while we're in the clean room? Is it to protect the clean room workers from the clean room and the dangerous stuff in the clean room? Or is it to make us look more sciencey and cool? There's a lot of nodding heads, good. Is it to protect the clean room from the workers? Or is it all of the above? So could I have a raise of hands for number one, please? Yeah, we've got a few, cool. What about number two? Okay, there's still a few hands, thank you. And finally, number three? Yeah, lots of hands, well done. And number four, all of the above? Brilliant, yes, we do wear them to look cool. But predominantly we wear them to protect the clean room from ourselves. Humans are quite dusty, which sounds horrible, but we just shed skin and stuff as we work. And the problem is that skin flakes are very big, and the transistors that we make in clean rooms are very, very tiny. But how tiny are they? Does anybody recognize this computer? Does anyone want to tell me what it is? Yes, well done, ZX Spectrum. So, 1982 computer. I had to kind of guess a little bit. The information on the internet wasn't great, but about 16 kilobytes of storage on there, not even a Word document. 48 kilobytes of RAM, basically nothing. And on the CPU inside the ZX Spectrum, we have about 8,000 transistors. And a transistor really is just a little electrical switch. It's not like a big mechanical switch that you move with your hands. You open and close it using a voltage. And your transistor count is roughly a way to measure how powerful your computer is. So does anybody recognize this? Sorry, say that? Yes, indeed. I spent quite a lot of happy hours playing Lemmings on the A1200. But again, 512 kilobytes of storage, it's not even a song, and 2 megabytes of RAM, just eat that booting up. But we are up to 300,000 transistors, so things are starting to get a little bit more impressive. Then we get to what I consider kind of the start of the modern computer, which is the XP era. And we're up to 40 gigabytes of storage, which is becoming reasonable. 256 megabytes of RAM, yeah, it's okay. 300 million transistors, lots and lots of transistors, great. But now, modern computers, we're all the way up over here. 2 terabytes of storage and 32 gigabytes of RAM. We can do lots and lots and lots with this. And part of that is because we now have 30 billion transistors in our computers. 30 billion from 8,000 about 40 years ago. And obviously, the transistors in this computer over here cannot be the same size as the transistors in this computer over here. They've shrunk and shrunk and shrunk and shrunk, following roughly a rule or an observation known as Moore's law, which is that roughly, and it's just about holding, the number of transistors on a chip doubles every 2 years, approximately. But we're getting to the end of that. We can't go much further. And the reason is because our modern transistors are now so tiny, 20 nanometers across. And if to try and visualize how small 20 nanometers is, if you imagine yourself, and then you take one of your hairs and compare how wide you are to the width of your hair, and then do that again with your hair. Imagine scaling your hair up to the size of yourself, and then comparing that hair to the width of your own hair if the hair was your size. Are you following? Yeah? No? They're very, 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 very tiny. You can get 5,000 of them across a strand of hair. Very tiny. We're approaching the atomic limit. Patrick, who will be on next, will give us a small idea about where we might be going beyond scaling with this. And I hope this has piqued your interest for some electronic engineering. And that's it. Thank you very much.
Right, okay. Right, afternoon. Just making sure, yeah, I'm definitely on. So, next talk. My name is Professor Patrick Degener. I'm a professor of neuroprosthetics, which is a mixture of electronic engineering and also brain science, if you like. So my research area, which I'm not going to talk about, is in trying to make blind people see again through little chips implanted in their brains. But one of the things I do want to talk about is this concept of mixing electronic engineering and what we understand of the human brain, because this is going to become increasingly important for all of us in the future. Now, here's a little video. Cute dog. Yeah, cute little doggy. This is a Chinese robot from a company called Unitree, and it's their little Go dog. It's their kind of the cheaper variant, but it's kind of the cuter variant. So, as a first question, yeah, you know, some of these future robots could be potentially scary. Some of them could be nice. Hands up who thinks that this little doggy is cute. Hands up who thinks it's scary. That's about half and half, okay. This is the cute robot. I can show you videos of scarier robots, but I won't. If we think about the future, there's going to be fewer and fewer young people compared to the number of old people. And it's quite simple. Medicine is getting better, so people are living longer. And then there's this question, well, who's going to look after the older people? Yeah. And one of the interesting possibilities is actually in terms of robots. You could have, for example, robotic dogs, you know, going out to, you know, carry your shopping, you know, walking beside you. That will carry your shopping as you walk home. Or that could potentially help blind people, you know, guide. Rather than having a, you know, a physical guide dog, you could have a robotic guide dog. Yeah. So there's many possibilities in the future. These things are only getting more and more powerful. We will see them in the coming years, in the coming 3 to 5 years, basically everywhere. If you go to China today and you're hungry, yeah, You don't get food from the hotel anymore. You ring up the local, the food company. The food company delivers to the hotel, and in the lobby of all the hotels, there's these robots, and the food company opens a little door in one of the robots, puts the food in, closes the door, and types your room number. And the robot comes to your room, rings the bell in your room, and then hands you your takeaway. Yeah? That is how it works in China these days. Yeah? And that is essentially the future of many, potentially our Amazon delivery and all the rest of it. Now, when we think about robots, yeah, we can think, again, we've talked about different types of engineering. And I would always encourage students, if you are thinking about different types of engineering, always go for a core engineering type. Electronic engineering, mechanical engineering, chemical engineering. And then if you want to specialize in biomedical, then you do that a little bit later. But if we think about the battery packs, this is chemical engineering. How do we make better batteries, more compact batteries? Because these robots are small, they've only got a certain limited amount of space and weight capacity. So we need to make the batteries efficient and carry more power. In Jenny's work, she described before these artificial hands, yeah. But that's personalized robotics. But in normal robotics, we also need more advanced motors. Motors that can give the agility of that little jumping dog from before, but also to achieve more, more compactness and more load. And then there's the sensors. How many senses have we got as a human being? Go on. No? That's what you learn in school, and it's wrong.
10,000?
No. A little bit less than 10,000. At the back? Okay, shall we go through them? Yeah? What's this? Smell. Yeah? What's this? Hearing. That's 2. What's this? Taste. That's 3. What's this? Sight. That's 4. What am I missing? Touch. Now, touch is actually 2 distinctive senses. You've got thermal touch and mechanical touch. You can feel temperature and you can feel pressure. Yeah? So that gets us up to 6. What am I missing? What am I? Balance. We have a special organ called the vestibular organ in our inner ear, yeah, that allows us to sense balance, yeah, even when our eyes are closed. So actually we've got 7 senses. You could argue maybe 6 if you put touch into one sense, yeah. Now, for a dog, what's the most important sense for a dog? Oh, okay, yeah, smell. So, if you wanted to make a smell sensor, for example, that would get back to the chemical engineering. And we heard Vangelis talk before about these kind of interesting chemical sensors. But in all of these components, I would argue, being biased, I would argue that actually the most important thing that we need to develop in the coming years is actually the brains for these robots. Yeah? And I say that because you young ones are going to be growing up over the next 5, 10 years wanting to go into the workplace, and developing better artificial intelligence, better platforms, computational platforms for that artificial intelligence is going to be really important. So, I'm going to try the impossible. I'm going to try and teach you guys the concept of artificial intelligence in 4 minutes. Let's try this. Picture. Yeah, this is the blind hiker. A blind hiker, being blind, yeah, doesn't know whether he's going up or down. The only thing he's got is a little talking altitude meter. Could be a she, but I've drawn it as a he. He's got a talking altitude meter that tells him what the height is. Okay? So this blind hiker goes hiking. And as he goes hiking up and down the hill, the altitude meter tells him some numbers of his height. How would he know whether he's going up or down? Yep, at the back, sorry, blue t-shirt. No, yourself, you're looking, yeah, go.
Because it goes from 0 at the lowest, then 1 and 2, then etc. until it gets to 9, which is nearly at the top, then it goes back down again.
So if he's at point number 3, how does he know he's going up or down? No, the altitude meter tells me he's at number 3. Sorry, yeah?
It can be decreasing or increasing. So you can
How does he know it's decreasing or increasing?
by just sort of like going up and then going down and then seeing where the numbers are going.
So what would you do with the numbers?
You could like see if it's going to if you're at 2,
Yeah.
you can see if it goes to 3 or 1.
Okay, so what would you do? What's the mathematics?
So if you're adding or subtracting.
Subtracting, yeah. You subtract the previous number from your current number. Yeah? Everybody get that? Very simple. Subtract, yeah. Adding it. And this is, look, a lot of people working in the AI domain will give all sorts of complicated equations. Yeah? But don't worry. It's just adding and subtracting. All of the really complex equations in the AI domain, some of the AI guys will get angry at me for saying this, is actually just lots and lots of adding and subtracting and a little bit of multiplication. So, depending on where you are, yeah, let's say you're at point number 5, yeah, and you subtract 4, what would you get? 5 minus 4? 1. Or let's say you're at point number, over here at the 6, point number 6. 6 minus 7? Negative 1, minus 1. Yeah? So what's going up? Plus 1 or minus 1? Plus 1. What's going down? Minus 1. Now, if our brains were doing this, yeah, up is plus, minus is down. If our brains were doing this, our brain consists of brain cells. So, these cells are called neurons, yeah? And what the neurons do is to simply look at the two numbers, the current number and the previous number, and do a subtraction. Now, the one problem with brain cells is that their output can only be a plus or a 0. Yeah? Bit like digital, bit like chips. They can't have minuses. So what we end up having is just lots of brain cells. We have an up brain cell and a down brain cell to do the calculation. Yeah? And that, in a sense, that very, very simple type of calculation is how our brains work, and essentially is the basis for all of the, the structures that we use for our AI. Except that instead of just having 2 inputs, we have lots of inputs. Yeah, lots of calculations. But the calculations themselves are actually really easy. They're just adding and subtracting. Yeah? So, this comes to my final point. So, Johannes did this brilliant sort of review of computing. And I had a Commodore 64. That was the big rival of the ZX Spectrum. But I did have the Amiga, so I was happy to see that. So, computing has progressed over the years. Has anybody built a computer? Whoa, with your son? Did you do it together? Ah, yeah, I tried to build the last computer with my son, but he got bored and walked off. To be fair, he was young, he was only 10. Now, for any of you who have built your own computers, or may build your own computers, up until now, there were 2 key components. There was the central processing unit and the graphics processing unit. And what all of these big AI companies have been doing up until now have been using these graphical processing units in a kind of a reverse engineering way to do the AI calculations, because a lot of graphical calculations are a little bit like the calculations used in AI. But, we can't have nuclear power plants dedicated to just one AI, company. You can't have vast amounts of power. We've got to make this process more efficient. So, now the big process in the coming few years is how do we make microchips that work more and more like the human brain? And this is the big new field coming forward in the coming years. And that will then power these robots and make them actually, well, a little bit more like us humans. To be supportive or maybe a little bit nasty, but that is technology. Yeah? Every technology has positive elements and negative elements. Yeah? So that, I would argue, is one of the biggest new areas of growth, if you like, in technology in the coming years. Now, in these last few minutes, I intend to give a live demonstrations. Hands up who's got raffle tickets? Have you got all your raffle tickets? Now, how am I going to decide which number to pick? I need to develop some way of generating a random number. So I don't have a raffle system with me. So what am I going to do? I'm going to generate it. Except, oh, right. This is a system called Visual Studio Code. We're going to do coding together. Hands up who's done any coding? Oh, wow! Loads of you. Right, well, we're going to do this in a language called Python. Hands up who's programmed in Python? Oh, a few of you. Right, hands up who hasn't programmed in Python before. Right, so what do we want to do? We want to generate some, what do you want to do?
We need to generate some numbers and we need to find appropriate pieces of text.
Okay, we do. Now, what are the numbers? Who's organized? What are the numbers? Okay, give me a second. So what we want to do, yeah? Okay, yo, AI, please help. Yeah. I want, no, I don't want to, I'm not a beginner, but I want to create a raffle, yeah? Because I have lots of clever kids who want a prize, yeah? How many prizes have we got? 1, 2, 3, 4, 5. Okay, so, oh, what's it saying? No, I don't want to pick one. Yeah, I have 5 prizes. Yeah, and I have 2 sets of children. Yeah, with raffle tickets. Yeah, between, what are the numbers?
136.
Yeah, 136 and 205. Sorry, it's between 136 to 205? Okay, and what's the second set?
361.
Okay, and 361
410.
to 410. Between, okay, yeah. Please generate, oh, I want to draw, oh, yeah, nope, from, not each set, but from both sets. Yeah, of children. Yeah? Oh, right, okay, we're on a roll. Oh, look, it's generating the code for me. Woo! What's going next? Ooh. Let's see. Oh, no, it's thinking. It's come up with something. First set. Okay. Set the range tickets. Are you thinking? No. Yeah, oh, here's the second set. What do you want me to do? Draw. Oh, yeah. First set of winners. Okay. Every time it does this, it does something different. So. Okay. Print the tickets. Okay. Print. Okay. Print. And we need to print the winning tickets one by one. Oh, whoop. Here we go for iron range. Oh, here we go. Here's the main program. Right. Oh. For iron range. Oh, this is second range. Oh, no, this is not good. It's got it wrong. It has got it wrong. So, hold on. What are we going to do? Right. Because demonstrates it didn't like the fact that we've got 2 sets. So we've got for iron range 1 to 5. Ooh. Okay, no, that's printing in a different way. Okay, right. So that is it. We are going to try and run this code. What's going to happen? Oh, I need to save it. We'll call it YoAI. Yeah, here's the program. And right. Okay, so we've got 5 sets. We're going to use the first set. Hansberry's got 192. Yeah. Okay, come down. Yeah. Come on down. Don't worry, I'm not going to eat you. Yeah. The set, who's 185? Is somebody got 185? Yeah. Is that yes? Do you want to come? Sorry? We're going to take the top. We're going to take the top row. Yeah, I know. I'm going to take 2 from the top set, 3 from the bottom set. Yeah. Right. Come down. So 185, 394. Who's on 394? I'm going to take. Sorry, it's going to have to be these 2 and these 2 because the AI was being a bit. Yeah. And 364. No? No 364? Yeah. Okay, come down. And 385. Right. Okay, so are you coming down? We're gonna finish this exactly on the 6 o'clock. Now, the demonstration there was that the moment that you try to do something a little bit more complicated with the AI, that you try to do 2 sets, things start to break down. Right. Here we go. Yeah, here we go. Brilliant. Here we go. And here we go. And who are we missing? Oh. Right. Okay. Yeah. Don't worry about the ticket. Okay. Right. That was my live demo. Thank you very much for coming. If anybody has any questions, please come down and talk to us afterwards for all of our speakers. But other than that, enjoy the rest of your evening.
Thank you. Thank you.